got rocket engines, you've got money. So get yourself on down to your nearest ex-Soviet state while stocks last.
RD-170s, NK-33s, we know how to build them and you don't. We've got warehouses of these things, but better be quick, the Americans are snapping them up as we speak. Want to hire our engineers to design your own engine? We can do that too. Better hurry before Iran get hold of them. Or maybe you're a country of taste. We've got hydrogen LOX engines just for you. The Brits are eyeing those up for their spaceplane, which they're totally going to build. Forget engines, how about an entire Buran orbiter? We already have some rich guy in Australia buying one, and we can make it happen for you too. Suitcase nukes? No, we don't sell those. I mean, they don't exist. Probably. Or a trip to Mir. Not ambitious enough? These Americans are already lining up to buy Mir. If you don't want to go there, why not bring it to your doorstep? We've already sold one engineering mock-up to, Tommy Bartlett's Exploratory in Wisconsin. Okay, and we can sell one to you too. The Europeans are eyeing up our VMT Atlant for their spaceplane, which they are totally going to build. Hell, have two of them. You buy one, you get one free. Please buy them. We really need the money. If we can't sell it, we'll rent it to you. Want to rent Baikonur? Be our guest. You can borrow a Soyuz or a Proton while you're there. Want to use it to be the first space tourist? Be our guests. We're already renting out our nuclear icebreakers to tourists. We can sure as hell take you to space too. Need to lift and shift something big? Well, this girl is for hire! Some people on the internet got something slightly wrong, so I've made an hour-long video about it. Back in 2020, a test firing of a SpaceX Raptor engine exceeded 300 bar of chamber pressure, which may have been a record at the time. It's difficult to know for sure. Chamber pressure isn't really something that was scrutinised in the public eye until quite recently. Quite a few news sources stated the previous record was held by a mythical and absolutely revolutionary engine, the late Soviet RD-701. Even Wikipedia still states that to this day. Problem is, on further reading, it's clear without a shadow of doubt that the RD-701 never existed. The first rule of my channel is to make videos about things that are interesting. I also have a kind of hidden rule to only evaluate things that were actually built. But the RD-701 is interesting enough for me to break the second rule. So this video will be a little different to normal. I will be discussing multiple things that were built that were closely related to the RD-701. And I will discuss how the RD-701 would have worked and why it would have been really difficult to actually use in an orbital spacecraft. I will try and let you come to your own conclusions on whether it could have given the world a cheaper, safer, and more practical space shuttle. For that, we need a lot of context. This video is a story. If you're here to just learn about how a sequential tripropellant engine works, just skip to the relevant chapter. Now, I want to be clear. Nothing here is a criticism of anyone who mentioned the RD-701 in a video or an article or anything else. It took me a while to realise it was never actually built, and it was only when I translated some journal papers originally written in Russian that I figured it out. It's just not possible to expect anyone mentioning it in passing as part of a greater video to have gone through all the research I did for this one. On that note, I'm pretty convinced the Wikipedia page for the RD-701 will be updated after I release this video. And that's a very good thing. Traditional sources, be they encyclopedias, books, privately owned news articles, YouTube videos, do not get this constant and open improvement. Almost every piece of written media has a mistake somewhere, and most of them are never corrected. Though I don't use Wikipedia articles as sources for my videos, I go into a bit more depth than that. It is an indispensable resource and encapsulates the principles of fair, free and transparent information that this channel is grounded upon. Finally, this story does tie into modern-day Russia, particularly the destruction of a prominent related piece of equipment in the ongoing conflict in Ukraine. I don't want to discuss that again. I've made my feelings on that unambiguously clear before. If you really want to hear it, skip to this point in the linked video. Whoa! The Soviets designed a tripropellant rocket. It must have been fueled by antimatter and cyanide or something, right? Well, not really. The RD-701 was designed to run on liquid hydrogen, kerosene, and liquid oxygen. For those who've seen the video I made about a year ago about a very different tripropellant engine, that's going to be a real disappointment. While that engine was a nightmare to operate from a chemical hazard perspective, the RD-701 would have been a nightmare from a mechanical and materials engineering perspective. To understand how it was to work, we first need to revisit an old concept: specific impulse. Shortened to ISP, specific impulse is one of the most important defining parameters for a rocket engine. It has a particularly interesting property, which is if you try and explain it on the internet, you'll always get angry comments telling you you've got something wrong. There's a reason for that. I'll get to it at the end of this chapter, and hopefully I'll make everyone angry. For a given propellant choice, specific impulse can be characterized using one measurement alone: the velocity of the exhaust. Imagine two equivalent rockets. Both eject the same mass through the nozzle, but rocket A ejects it at a higher rearward velocity than rocket B. Rocket A will travel faster. Rocket A has a higher specific impulse. Okay, how can we make the exhaust speed higher? The most obvious approach is to use lower density propellants. If the exhaust gases have a lower molecular mass, they'll be accelerated to a higher speed, pushing the rocket forward with a higher thrust. At the extreme low density end are propellants that incorporate hydrogen. Hydrogen and liquid oxygen is the practical example and the propellant of choice for systems where a high ISP is a necessity. We can actually do slightly better than this, but beyond this point are spoilers from our previous tripropellant rocket video. If you don't want to have that horror concoction revealed here, just skip forward 1 minute. Okay, so that engine used mainly hydrogen, but accelerated it by burning lithium and fluorine at extremely high temperatures to increase the exhaust speed even more. Crucially, those are all elements with low atomic masses, giving a low-density exhaust and delivering a record-high ISP. Now, if for some reason we wanted to build a rocket with a low ISP, we'd be best using a high-density propellant. What has a really high density? Mercury. If for some absurd reason we could get mercury in the exhaust, we'd reach the other extreme on this plot. But of course, that'd purely be a thought exercise, right? Here are some common propellants ranked by density with their ISP represented visually. Okay, so just use hydrogen and oxygen for every rocket, ever, right? It gives us the highest ISP, so we'll accelerate our rocket faster for a given mass of propellant. It's the most effective combination. Not so fast. That'd be true for a rocket just floating around in the vacuum of space and away from any gravitational influence. In reality, we need to actually build and launch our rocket from Earth. And that's where low density works against us. Liquid hydrogen is about 1/12 the density of kerosene. That means we need 12 times more volume to hold every kilogram of hydrogen. That means a lot more structure, and more structure means more mass that is not used for propellant and not used for payload. The engines need to be able to flow a much higher volume of fuel per second than those in a kerosene-based system. That means bigger turbo pumps and heavier plumbing. A high ISP rocket is a heavier rocket. We have a trade-off. And that is why the Delta Medium and its brother the Delta IV Heavy are the only rockets ever built that can get to orbit using only hydrogen and oxygen. Ever wonder why a Delta IV Medium can carry less than half the payload to low Earth orbit, yet is larger than a Falcon 9? That's why. Of course, this isn't a criticism of the Delta IV, it was a workhorse. But in most cases, using hydrogen-based propellants alone to get to orbit is not practical. So, a smaller rocket is a lighter rocket. Let's revisit the other end of that scale. That tripropellant I mentioned in the previous video is probably not the most chemically horrifying rocket engine ever built. It's definitely not the most horrifying one ever conceived. That honour probably goes to the dimethyl mercury rocket proposal. If you didn't immediately recoil in horror, a tank of dimethyl mercury would be enough to fatally poison every person in North America just by coming into contact with it. That was never built. But back in the 1960s, US researchers did inject mercury into a combustion chamber, giving us the most dense propellant ever used in practice, and presumably creating an environmental disaster in the process. So finally, we see why kerosene and methane are so common as rocket fuels. They're trade-offs between rocket mass and specific impulse. But for those willing to put in the extra effort, it is possible to have the best of both worlds. Using a higher density propellant for the larger first stage allows us to build something that isn't absolutely huge, but still has the high thrust needed to get off Earth without building giant heavy engines. The second stage of a rocket is smaller, so it's easier to build a hydrogen-fueled second stage that is actually practical. And if we burn hydrogen when we're already travelling at a significant proportion of orbital speed, that means more of that high ISP fuel is ultimately used to deliver energy to the payload and not to the fuel itself. This is why the shuttle and Buran used boosters to get as much hydrogen as high and as fast as possible. It's why the hydrogen-fueled Centaur upper stage has been used, well, everywhere. And it's why New Glenn uses a hydrogen-fueled upper stage. A smaller first stage to ultimately use a high ISP fuel to reach orbit. The RD-701 would have combined all of these advantages into a single engine. And just to make everyone, both American and non-American, mad before we move on, the reason specific impulse is often misunderstood is because it's usually expressed in a weird unit. Impulse is the change in momentum of a system. Specific refers to per unit of propellant consumed. So, per every kilogram of propellant consumed, the momentum of the rocket changes by a given amount. That amount is the specific impulse. You'll note this is independent of the mass of the rocket. I didn't make that entirely clear in my last video on the matter. Anyway, impulse, or change in momentum, is the speed multiplied by the system mass. Specific impulse is per kilogram, so we have a unit of meters per second. That is equivalent to newton seconds per kilogram. You can see me demonstrating that on screen, if you're really interested. So, expressing specific impulse in meters per second, or newton seconds per kilogram, is intuitive and really easy to understand. Unfortunately, America disagrees, because historically Americans have been allergic to using SI units. We end up with specific impulse being commonly expressed in seconds. This is because doing so works in both US standard and SI units. I tried to extend an olive branch in the last video by showing seconds as an okay unit to work with, but people got mad at me. So, there you go. Use whatever units you want. And for all the smug Europeans like me declaring, well, NASA use metric anyway. No, they don't. Why do people always say that? Here are some NASA papers I've used in previous videos, all in US units. In fact, the Apollo guidance computer had to use a fraction of its unbelievably precious memory to convert its outputs to US standard units, as the astronauts preferred it that way. Alright, I know people are still going to crucify me for that. In reality, NASA is a huge organisation. Some departments use SI units, especially for engineering calculations. Some use American standard units, especially for the likes of public outreach. And that's varied over time as well. You can see them using SI as a secondary unit in one of the papers I showed. As with the aerospace industry worldwide, they use a mix of units, which is, no further comment. And indeed, chamber pressure is often quoted in bar, which is a non-SI unit. I will be using that throughout this video, by the way, just to keep with convention. So, there you go. There are indeed 3 types of countries. Those that use metric units, those who've been to the moon, and Liberia and Myanmar, for some reason. With all that in mind, let's build a cheap orbital spaceplane. What better way to start off than by building an extremely expensive orbital spaceplane? Here is the shuttle. That's the one most of us are familiar with, but I'm going to replace it with Buran for reasons that will become apparent. Now, I did an entire video on Buran. I tried to stay kind of neutral in that video regarding whether or not I thought Buran was a good idea. It was a hell of a technical achievement, But let's be honest, building it was a pretty terrible piece of decision-making on the part of the Soviets. Exactly as with the shuttle, if used to launch crew, Buran would have been complete overkill, highly complex and failure-prone. If used to launch cargo, well, they already had a rocket for that. That said, to have ever had a shot at building what we're about to sketch out, they kind of had to build Buran first. So, how about focusing on just getting the crews to orbit and back? Let's aim for that new Mir space station. Without a requirement for a large cargo bay, we can shrink our orbiter right down, and that means less payload mass, so we can shrink the propellant tanks too. Let's consider what's in those propellant tanks. The side boosters use kerosene and liquid oxygen and essentially constitute a first stage. They provide a high thrust yet are relatively small. The core tank uses hydrogen and liquid oxygen. This was absolutely necessary to reach orbit for both Buran and the shuttle. No other practical propellant had the ISP necessary to get such a large payload to orbit. Okay, let's simplify things. We'll stack the two stages sequentially and burn the kerosene followed by the hydrogen. The orbiter could sit on top like the concepts we've seen for Dinosaur and Dream Chaser. But we can do better than that. This system needs to be cheap. And as is, we're throwing away all the expensive engines on every launch. So put the engines on the orbiter itself, just like the shuttle. But where do we mount the orbiter now? The only way this could work practically would be to mount the orbiter like this. And that's a problem, because we can no longer jettison the first stage. So don't. Incorporate all the kerosene and most of the hydrogen and liquid oxygen into a single stage. Burn the kerosene first, followed by the hydrogen. Drop that stage and use a very small amount of hydrogen and oxygen stored in the orbiter for the final orbital insertion. We can use the existing RD-58 engines for that final burn. They're extremely efficient and have a good flight history. But carrying that large tri-propellant stage so high represents a significant mass penalty. So we need to reduce the mass of our orbiter as much as possible. Instead of equipping it with separate kerosene and hydrogen main engines, could we somehow combine the engines into one? A single engine that first burns the kerosene and then switches to hydrogen. That engine would have been the RD-701. So, a different type of tri-propellant entirely to the one in my previous video on the matter. That one burned both fuels at the same time. The RD-701 would do so sequentially, but it's a bit more complex than that. During the kerosene phase, or mode 1, a small amount of hydrogen would actually be added to the mix. And during the hydrogen phase, or mode 2, a small amount of kerosene would be added. The RD-701 would have therefore been a mostly sequential tri-propellant engine. We'll discuss why later. But this still wouldn't work. Even combining the highly efficient existing hydrogen and kerosene burning engines available to the Soviets wouldn't give us the speed needed to reach orbit. We need a bit of a boost. And the Soviets had just the thing for that. Every now and then, we humans build something that breaks a record. Something bigger, faster, or stronger than anything of its type. Once in a blue moon, just the right group of humans, for whatever reason, manage to get together and build something that doesn't just break records. In a single step, it exceeds them by such a margin, it creates an entirely new class of thing all by itself. There were cargo planes. There were strategic airlifters. And then, there was the Antonov AN-225. You can say what you want about the Soviet space program, but they were always at their best when they stopped messing about and trying to one-up the Americans and actually did their own thing. The AN-225 was about as far from messing about as it gets. Originally built to carry the Buran orbiter, it was the largest fixed-wing aircraft ever built by every meaningful metric. How large? The American shuttle weighed 30 tons more than Buran, and the Americans chose to modify two Boeing 747s, the largest aircraft available in the West, to carry their heavier orbiter. If you could break up one of the shuttle carriers into little pieces, the AN-225 could easily carry its entire mass internally. In fact, add the shuttle too. And that's not just a paper exercise, it actually flew with a heavier payload than that on at least one occasion. The system as a whole was to be called MAX. That stands for Multipurpose Aerospace System. Could the AN-225 have carried MAX? Does the AN-225 have a potential competitor in existence right now? We'll come back to both of those questions soon. So, we arrive at the in-detail description of the actual topic of this video. How would the RD-701 have worked? I'm going to be honest, I spent a lot of time pondering how the heck to even begin with this one. So let's begin where the Soviets left off. Thanks to the Buran program, they had two of the best rocket engines on Earth. The RD-0120 was a fuel-rich closed-cycle hydrogen liquid oxygen main engine. 4 of them were used on Buran. I've previously referred to them as copies of the Space Shuttle main engines. That's not really true. The Soviets most certainly did copy the materials and basic architecture from publicly available NASA data, but they also made fundamental changes which we'll discuss. Second was the RD-170. To this day, this is the most powerful liquid engine and one of the highest ISP kerosene liquid oxygen first-stage engines ever built. That's because it uses an oxidizer-rich closed cycle. As we build up our model on screen, I hope viewers who are unfamiliar with that terminology will begin to understand why that was a spectacular achievement. The Soviets copied many aspects of the shuttle main engines, so why didn't the Americans copy the RD-170? Because they had no idea it existed. They only learned of it when the Soviet Union collapsed. It's a hell of a story, and I discussed it in my video on Buran. Not to dwell on the point too long, but a joint paper from Energomash and Pratt & Whitney written shortly after the West discovered the RD-170 states the oxidizer-rich preburner and turbopump were the enabling technology for the RD-701. In fact, that paper's interesting. We are not too far from a universe where the RD-701 was developed jointly by the Russians and the Americans. It's probably fair to say the Soviets had done the difficult part already to bring this engine into reality. Well, the difficult part with respect to engineering anyway. Politics and economics are a whole different ballgame. I don't really like ball games, except for cricket. So, let's discuss something almost as exciting and complex as a 5-day test match. The RD-170 and RS-25 shuttle main engines are something I've discussed in depth before. If you want the details, the links are on screen now with timestamps to relevant chapters. This chapter is basically an amalgamation of everything I've discussed on rocket engine architectures before. For those happy to proceed, let's do a quick recap. The RD-170 burned a relatively small amount of fuel with liquid oxygen in 2 pre-chambers. This created a hot oxygen-rich exhaust which drove a turbine. For those that aren't aware, this is the oxygen-rich part. Designing a turbine that can survive that atmosphere was thought to be practically impossible in the West. The turbine drove a fuel pump which sent most of the fuel around the nozzle and combustion chamber to cool it, with the remainder sent to the preburner. On the same shaft was the oxygen pump which supplied all of the incoming liquid oxygen to the preburners. The hot oxygen-rich preburner exhaust was sent directly to the injectors in the main combustion chamber, where it mixed with the fuel, allowing combustion and therefore providing thrust. That thrust was actually through 4 separate chambers, but we're going to apply a little hindsight now. When most of the literature for the RD-701 was written, the Russians had not yet developed the RD-180, which is a half-sized variant of the RD-170. And side note, the naming terminology is confusing. I hope my on-screen guide is helping. Anyway, we're going to only consider that half-sized variant from now on, as it was similar in scale to the proposed RD-701. Okay, now let's look at the RD-0120. Unlike the shuttle's RS-25s, all the turbo machinery was on a single shaft, giving a simpler engine than those on the shuttle. How on earth this was viable, given the different density between liquid oxygen and hydrogen, I have no idea. But all the fuel and some of the oxidizer were fed into a pre-burner to give a fuel-rich exhaust. The exhaust drove the turbine and was fed into the combustion chamber. The turbine drove the fuel pump, which sent most of the hydrogen directly to the combustion chamber, with some routed around the chamber and nozzle through ducts to provide regenerative cooling, before being burned in the chamber. The first stage of the oxidizer pump sent most of the high-pressure oxygen to the combustion chamber. Some was boosted by the second stage and sent to the pre-burner. As was the case with the RD-170, all the fuel eventually ends up in the combustion chamber, giving a closed cycle. So, how do we mash these two engines together to make an RD-701? Okay, let's take the RD-180 as a basis. You'll note the RD-180 has two combustion chambers but is a single engine. This was to combat combustion stability issues from using a large single chamber. The RD-701 would have also used two chambers in the same manner. A derivative, the RD-704, was also proposed which would use a single chamber. That was even further from existing than the RD-701, so we need not consider it further. We take a pre-burner from an RD-180 and pair it up with a half-sized LOX and kerosene turbine. Again, with hindsight, this would be, in reality, the turbine assembly from the relatively new RD-190, a quarter-scale derivative of the RD-170. Okay, let's connect the kerosene pumps to our turbine. That is pumps plural. The first stage sends most of the fuel directly to the combustion chambers, and those chambers would operate at 300 bar, which is where that mythical number comes from. Some of the fuel flows into the second stage pump, which provides fuel to the pre-burner. Incidentally, prior to the Raptor, that chamber pressure record was likely held by either the RD-180 or the 190. They both operate around 260 bar, but have likely exceeded it during testing. Now, since the RD-701 was never built, we don't need to swoon over this fact too much, but the outlet of that second stage kerosene pump would have experienced the highest pressure anywhere in the system. About 940 bar. The oxygen pump would be on the same shaft, just as with the RD-180. This would send all the liquid oxygen to the pre-burners. Again, pre-burners with an S, because it would also supply oxygen to the hydrogen pre-burner. And now we know why the engines would have to burn at least some kerosene throughout the flight. It was to keep the oxidizer pump running. Okay, now it's time to move to the second mode and burn the hydrogen. Pratt & Whitney suggest a half-sized fuel pump from the shuttle main engines. I suppose a half-sized pump from the RD-0120 would do the job equally well. Let's stick with the Soviet/Russian design and take that. Though, bear in mind, the RD-701 could have very well used common components from the RS-25 had it been developed in conjunction with the Americans. That's something I rarely see mentioned. Depending on the paper you read, this turbo pump would have been driven either by a second oxidizer-rich kerosene pre-burner or by a fuel-rich hydrogen pre-burner. I'm going to go with the fuel-rich version, as this wouldn't require a fancy interpropellant seal here. Because on this shaft would be the hydrogen fuel pump. If the turbines were driven by oxygen-rich hot gas, sealing this shaft would be a complex undertaking. Not impossible, the RS-25s manage it. But we don't need to do it here, so let's not. The hydrogen fuel would be boosted by the pump, and some of it flowed around the nozzles and combustion chambers to provide regenerative cooling. Note, the cryogenic hydrogen would have adequate cooling capacity to negate the need for film cooling, as used on the RD-180. In conjunction with the closed cycle, that means all the fuel ends up in the combustion chamber, improving efficiency further. And now we know why some hydrogen had to be burned during the kerosene phase of flight. to keep the regenerative cooling active. So that completes the basic cycle. It's interesting to note the cycle itself doesn't change between the kerosene and hydrogen modes. Instead, the proportion of each fuel burned was changed, but the overall engine cycle would have been the same throughout the flight. Now, the final components we need to discuss are the low-pressure pumps. Each of the three propellants would have a low-pressure turbopump driven by a fraction of its respective high-pressure fluid. That gives us a total of 5 turbopumps, 2 pre-burners, and 2 combustion chambers. I haven't even touched on the complexities of balancing all the pressures in that system, monitoring it during flight, and testing, and indeed starting the thing up. But something like the RS-25 is probably around the same level of mechanical complexity as the RD-701. And the Soviets definitively showed they could build highly complex engines. On paper, the RD-701 works, and I have no doubt it would have been technically viable if actually built. But right now, we're looking at it as engineers looking at the RS-25 back in the 1970s. That looked perfect on paper. And it is as close to perfection as it gets in reality, speaking solely as an engineer. But with 40 years of experience, we now know the RS-25 costs a fortune to build and reuse. I have no idea whether the RD-701 would have been equally, if not more, expensive. I suppose a tantalising fact to end the chapter on is that when Pratt & Whitney engineers visited Russia in 1991 and viewed the RD-0120, they eventually invited the Russians over to the US. The RD-0120 had a number of design features such as milled cooling channels, the single shaft and the improved chamber geometry, which could feasibly have drastically reduced both construction and rework costs for a relatively small reduction in ISP compared to the RS-25s. Maybe the RD-701 could have actually been economically viable. Well, I suppose this is the disappointing chapter. This is where I conclusively demonstrate that the RD-701 was never actually built. On the plus side, the Russians did build a kerosene, hydrogen, oxygen tripropellant engine, but the paper that documents that also confirms that the RD-701 never existed. NPo Energomash was formerly known as Design Bureau OKB 456 back in the Soviet days. Its chief designer was Valentin Glushko, one of the 2 prominent Soviet rocket engineering geniuses. The other was, of course, Sergei Korolev. They hated each other, by the way, but that's another story. Back in 1968, Glushko founded the publication of recent proceedings from the Bureau, and this eventually became the annual proceedings of Energomash. Typical issues consist of several dozen technical papers and contain some of the more interesting aspects of Russian rocket development. Now, I tried my damn hardest to find copies of those proceedings from around 1988, which is when development of the RD-701 was underway. This included searching the catalogue of the Russian State Library, looking through Energomash's archives via the Wayback Machine, blocked in the West now, unfortunately. Artem even tried emailing Energomash. The earliest issue I could get was the 18th proceedings, published in the year 2000. It's fair to say that things went a bit sideways in Russia during the 1990s, and unfortunately many documents were lost or simply never digitized. But what seemed like a dead end turned out to be a real stroke of luck. That proceedings contains the paper 2-mode engine with 3-component fuel for a new generation of aerospace systems and launch vehicles. 12 years after the RD-701 was conceptualized, this paper was published, and it documents the test firings of a progenitor to the engine. Now, let's not get too excited. This test engine was a far cry from the actual RD-701. It consisted of a thrust chamber and nozzle plumbed up to external hydrogen, kerosene, and liquid oxygen supplies. Regenerative cooling was not fully implemented. A water jacket surrounded the thrust assembly. The liquid oxygen was supplied through an injector at the top. A small amount of kerosene was mixed with the incoming oxygen in the pre-burner chamber, which would supply hot oxygen-rich gas to the main chamber. The fuel was injected into the main chamber by injectors around the outer diameter. To simulate Mode 1 operation, liquid hydrogen was provided via this line, and this bypass valve was opened to allow kerosene in via this line. To simulate Mode 2 operation, the kerosene bypass valve was closed, allowing only liquid hydrogen into the main chamber, though some kerosene still flowed into the pre-burner chamber. You'll notice this is simpler than the proposed flow control for the RD-701, where throttle valves would only allow a small amount of hydrogen through in Mode 1. For this test, the hydrogen flow was at full rate throughout. There was none of the complex turbo machinery present for an actual rocket engine here, and based on the thrust results, the scale of this article was only about 1.5% the scale of the RD-701. It produced around 60 kilonewtons of thrust in Mode 1 and about 30 kilonewtons in Mode 2. By the way, that isn't exactly a small amount of thrust. The RD-701 was intended to output 4 meganewtons in Mode 1. For context, the F1 engines on the Saturn V output 6.9 meganewtons each. This high thrust requirement is the reason the chamber pressures would have to be so high. The test engine was fired a total of 44 times with different hydrogen and kerosene mixtures tested, along with variations in the cooling jacket and the injectors. Many of the firings included a switch from Mode 1 to Mode 2, and the longest firing was for 100 seconds. The main goal of testing for efficient mixing and combustion of the three propellants was achieved. The highest chamber pressure recorded during the test was 220 bar, which is surprisingly high for a first-pass engine test. And of course, the tests confirmed a single engine could be built which handled both the material requirements for an oxygen-rich turbine exhaust and cryogenic hydrogen fuel. It stated that the planned next step would be to improve the mixing heads further and incorporate regenerative hydrogen cooling in a larger test engine. But it seems that despite the early success, the work never went any further. The common narrative seems to be that the RD-701 itself was built and tested on a stand during the final couple of years of the Soviet Union. This paper shows that by the year 2000, the most advanced Russian tripropellant engine was the one discussed. Nothing of note on the matter has been published since. Oh boy, was I wrong there. 2 weeks before releasing this video, someone uploaded a ton of information to the Secret Projects forum. I almost had to significantly delay this video and rewrite the script. It turns out there was another hydrogen-kerosene tripropellant engine tested in Russia. On further reading though, that too was just a test stand article. It was much larger than the test engine we discussed, and it was apparently funded by NASA, though the source for that is a magazine entry, so I can't definitively confirm it. Okay, so this tripropellant engine was designated as the RD-0750D. The RD-0750 would have been a simplified version of the RD-701. It'd use a common pre-burner for both fuels feeding into a single turbine. No idea how that'd work in reality, by the way. The test article which actually existed, that was the D variant, that lacked the kerosene pump. So kerosene was supplied from an external system. The new pre-burner and kerosene pump were fitted onto an existing RD-0120, which is why in this photo of the test engine we see the RD-0120 markings. The engine was test-fired in April of 1998, but after 4 seconds an automated system shut it down. Inspection revealed the pre-burner and turbine had essentially destroyed themselves. Some improvements were proposed based on this, but it's unclear whether a second test engine was ever built and fired. So there you go. There was actually a second tripropellant engine built in Russia. It was much simpler. It was essentially an RD-0120 with a few bits and pieces bolted onto it. Had it been finalised, it would not perform as well as the RD-701, which had a dual shaft and dual pre-burners, but it did apparently exist to some extent. Oh, and also it didn't work. Crucially, the overall theme of this video remains true. The RD-701 never existed. But let's go back to that 2000 paper regarding its demonstrator. The paper even puts dampeners on a couple of other myths. You may have seen this photo of a supposed RD-701. Here is that exact photo in the paper, with a caption reading RD-701 mock-up. I believe that mock-up is still on display in Moscow. And here's another common image of mock-up RD-701 nozzles on a model of the aft end of a Max spaceplane. Now, the other argument I'd anticipate is something along the lines of, The Soviets or Russians would never reveal something this clever to the world. They must have built the RD-701 and kept it secret. Really. Ignoring the fact that they published their work on the concept to date in 1993 in conjunction with US engineers at Pratt & Whitney, let's go back to my intro. Yes, I presented it in a daft way and it was a lot of fun to make. But every example of hardware I presented there was a true story. When the Soviet Union fell, the member states couldn't sell their IP and hardware to the West fast enough, and the West eagerly bought it all up. To theorise there was some kind of super secret engine which actually wasn't secret but was still built anyway would just be delusional bad story writing. For anyone that remains unconvinced, it's impossible to prove something never existed. But I have provided evidence that it didn't beyond all reasonable doubt. If that doesn't convince you, nothing will. Moving forward though, the bench tests were successful. The concept of the kerosene, hydrogen, oxygen tripropellant is not just fascinating, but still in 2025, it's potentially revolutionary to spaceflight. It still exists on paper, just waiting to be dragged into reality. When I started research for this video about a year ago, I initially believed there was only one major technical obstacle to Max, and that was the air launch aspect. We now know there were two, the other being the engine itself. So let's take a chapter away from the engine to ask the question, could the AN225 have launched Max? I'll cut to the chase. I think it could, but it wouldn't be easy. I'm also extremely biased because I loved the AN225. Let's start with the most obvious requirement, payload mass. Though the AN225 was designed to transport the Buran orbiter and Energia components, it's rarely mentioned that it was actually designed from the start as an airborne launch platform. NPo initially proposed a 170-ton vehicle to be launched horizontally from the AN225, but the mass was later revised upward to 225 tons. Apparently that's where the 225 in AN225 comes from. Max was conceived shortly after the breakup of the Soviet Union and was the next revision of this launch system. The launch mass for Max would be 275 tons. Now, we're going to get to what rated actually means in a second, but the maximum rated payload for the AN225 was 250 tons. And it did exceed this on one occasion during a record-breaking flight, which saw it carry a 253.8-ton payload consisting of 5 T-72 tanks. So, we know the AN225 could fly carrying just over 250 tons internally with relative ease. In fact, one test flight carried a 250-ton internal payload at 763 km per hour. It was designed to carry 225 tons externally. Could it manage 275 externally? There are many factors to consider here, but we'll just cover the two main ones and come back to some others at the end of this chapter. Considering payload mass alone, the 250-ton rating would be based on structural loading. Exactly how and where that load was applied to the fuselage would be limited to specific cases, but I can't imagine re-rating the entire structure to carry an extra 25 tons would be too much of a challenge. If a specialised AN225 was constructed just for the purpose of max launches, which is what Antonov proposed, necessary strengthening for the orbiter load case could be added, and I imagine weight could be saved by removing structure from elsewhere. For example, the strengthened floor in the internal cargo bay would no longer be needed. The second major consideration is the overall takeoff mass itself. It's no good having the structure able to bear the weight of the orbiter if the aircraft can't even get off the ground. It's difficult to determine what the max external load the AN225 was rated for was, as the mass would have varied with cross-sectional area. Physically large loads would add additional air resistance. But the maximum rated takeoff weight for the AN225 as a whole was 640 tons. Though do note this was increased from 600 tons following modifications made in 2000. It flew at least twice with a takeoff weight exceeding 630 tons. With an empty weight of 285 tons, a 275-ton orbiter would leave just 80 tons for fuel. That'd give a flight time of just 4 hours. Not enough to climb to the 8 kilometers or so launch altitude and reach a safe launch zone and return with contingency fuel. The D18T turbofan engines on the AN225 were quite performant for their time, so we can basically rule out uprating those. Okay, and recording 4 weeks after I said that, it turns out I'm wrong there. We'll come back to that in a second. Quite a few I was wrong moments in this video, aren't there? I think I've got them all now. Check for a pinned comment in case I find any later, I guess. Researching things that don't exist is difficult. The only real option to carry Max to its launch altitude, therefore, would be to relax the ratings to get an extra 50 tons or so of takeoff weight. I'm not exactly sure what the limiting factors were for the AN225 ratings, but they'd include factors like worst-case scenario crosswinds, ability to continue flying with the loss of engines, runway length, and a combination of many others. I'm sure relaxing some of these constraints would have given engineers the extra 7% extra takeoff mass they needed at the expense of some added risk, or by limiting the locations and conditions in which Max could be launched. Having strict limitations on launch conditions is extremely common for spaceflight already. For an extreme example of relaxing ratings to get a job done, we only need to look at the AN225's predecessor, the VMT Atlant. That required a 3.5 kilometer runway and really was operating at its limit when carrying the heaviest design payload, a stripped-down Buran orbiter. But it flew some 150 ferry flights successfully. It even managed to carry out a successful landing while carrying that worst-case payload and after a double engine failure on the same wing during final approach, though I am certain some heroics on the part of the crew were to play there. Those watching the screen right now are probably wondering why I've gone to the trouble of building a model and chroma keying it. Well, there are a few reasons. First of all, it's fun and cool. Secondly, for this particular video, I wanted to improve on this really badly green-screened Molniya orbiter and AN225 from an original Soviet informational video. There's a deeper reason that I sometimes make these models when I have access to Artem's excellent 3D modelling, and yeah, I can do some 3D modelling myself too. First of all, it's not actually necessarily easier to make a digital model. This may be surprising, but those animations take ages to make. But more fundamentally, when I make a video, I always try and put my hands on something related to the main topic. That can involve a museum visit, it can involve buying things on eBay, or it can involve a physical model. The AN225 here is from a kit. I had to 3D print the orbiter and the tank. I don't think anyone sells a model of those. I printed the propellant tank first, and as the print began, I stopped and discarded it. The scale was clearly wrong. That tiny little diameter was obviously too small. I'd messed up the scaling. So I got the calipers out and measured it, and realised with almost a sense of dread, my scaling wasn't off. The propellant tank wasn't too small. It was just dwarfed by the AN225. I'd never got that sense of scale from the on-screen 3D models, and I can't communicate it to you through your screen. No doubt the only way I could have ever appreciated the scale of this thing would have been to see the AN225 in person. And while we're discussing it, I am more than aware that the colour scheme on my model is, I suppose you could say, historically inaccurate. The digital models we've used here show what Max had looked like if it was flown by the Soviet Union. The decal set that came with my model included the really cool-looking Ukrainian colour scheme. So we could imagine here a Russian orbiter on the back of the Ukrainian AN225, a kind of post-Soviet Union collaboration. Sounds impossible today, but the Russians and the Ukrainians did manage to collaborate just fine on sea launch, so it's not outside the realms of possibility. Anyway, what else would need to be added to the AN225 to allow it to function as a high-flying launch platform? NPo Molniya concluded an 8-ton suite of hardware would be needed to provide launch support. I suspect the removal of internal cargo handling equipment, such as the hydraulic systems for loading, the strengthened floor, the internal cranes, the loading door, would exceed 8 tons. So I doubt this launch suite would eat into the mass budget as such. A component of those 8 tons were 2 additional crew members. I should probably say at this point, the safety implications of Max really make me quite uncomfortable. The orbiter itself would be fitted with ejector seats for the crew, but as for the crew in the AN-225, I'm not sure. I'm not even sure it would be possible to eject and clear such a large aircraft. And it's hardly unlikely one would blow up before or during launch. Just last week as I typed this, a Chinese rocket blew up on a launch pad. And Max was fueled in part with hydrogen, which leaks everywhere. During fueling and taxiing, it would not be possible to include advanced hydrogen venting systems like those seen on the shuttle or the Delta IV. So the risk of explosion would be high. Even if it were possible to remove the crew entirely and automate the thing, an accident would be disproportionately expensive if it took out an entire AN-225. One necessary addition would be a propellant venting system. If this system were used regularly, it would be inevitable launches would periodically be scrubbed after the aircraft had left the runway. Now, the thought of launching this thing makes me uncomfortable. The thought of landing 275 tons of hydrogen, kerosene and liquid oxygen on the back of an aircraft originally rated to carry 250 tons of less volatile stuff is a solid no from me. And Antonov agreed. The AN-225 was therefore to be fitted with vent valves and pipes which should sequentially vent each propellant to atmosphere via the tail in the case of an issue. Amazingly, there is a precedent for something arguably even more sketchy than this, and it very nearly actually flew. It's the space shuttle. Remember the hydrogen-fueled Centaur upper stages I mentioned at the start of this video? That was due to fly in the cargo bay of the shuttle to launch the Galileo probe to Jupiter. But then the Challenger disaster happened, and NASA re-evaluated the idea of flying several tons of liquid hydrogen and oxygen in the cargo bay of a crewed orbiter with no launch escape system. But the Centaur would have also been connected to external vents used to dump the propellants in the case an emergency abort was performed. Apparently, the astronauts were not thrilled with this idea and feared the jettisoned hydrogen would ignite. But back to Max. Most animations show it igniting its engines before separation. This was the cause of a particular heated debate between Antonov and Molnier. On one hand, igniting the engines before separating would allow any issues to be diagnosed and the launch aborted if necessary. On the other, even with them angled away from the aircraft, that is a lot of radiant heat. Unsurprisingly, Antonov, arguably the best aircraft designers of all time, were correct. They mounted a test section of fuselage the correct distance from a test engine and observed it melt within seconds. So, I think if Max ever saw daylight, it would have separated from the carrier and then ignited. Not only would that reduce the risk of destroying the carrier aircraft if an engine failed catastrophically at startup, but it'd also mean no thermal shielding would be needed to be mounted on the carrier, saving a little more mass. This relates to my engine comment from a few minutes ago. To release Max prior to firing the engines, the AN-225 would have to perform a pitch-up manoeuvre followed by a hard bank after release. Amongst other requirements, that would require quite the degree of agility in an aircraft near its service ceiling. It was determined the AN-225 could manage this at a maximum altitude of 8.5 kilometres, and that would be cutting things really fine if Max were actually to make it to orbit with any payload. The design proposal for Max was published in the early 1990s. The AN-225 was designed in the early 1980s. In the intervening 10 years, a slightly uprated version of the D-18T engines was made available. But the proposal document gives preference to building a special version of the AN-225 with Rolls-Royce Trent turbofans. They would allow for a release at 10 kilometres of altitude, easily enough to get to orbit. It's fascinating that we aren't too far from a present day where Russia, Ukraine, the US, and the UK all work together to completely change spaceflight 20 years before the likes of SpaceX. The AN-225 had a few other design aspects going for it which I think strengthened the case it would be a feasible launcher. The first was the aerodynamic design. I briefly mentioned in my Buran video that it would be a fallacy to just consider the aircraft as big and dumb. It incorporated multiple technologies which were state-of-the-art at the time. Physical wind tunnel testing was augmented with computational simulation, which was very much an emerging technology for aerodynamic design in the 1980s. The final result was an airframe whose appearance may deceive you. The lift-to-drag ratio of the AN-225 was 19. That's remarkably high for any large aircraft of its day, never mind a cargo aircraft. For comparison, the Boeing 747-400 has a lift-drag ratio of 15.5. The Airbus A340, which flew 4 years after the AN-225, has a similar ratio, but that has 2 less engines and is a different class of aircraft entirely. Another consideration is the presence of fly-by-wire, something very new for an aircraft at the time. For carrying outsized loads, some form of augmented stability eventually becomes essential as the size of the load increases and affects the vehicle flight characteristics more and more. The only reason the VMT Atlant was flyable was the addition of a mechanical stability augmentation system. But the AN-225 had quadruply redundant flight computers controlling the pilot input to all the major flight surfaces. It also had power-by-wire. That is an electronic link between the pilot's throttle controls and the engines. These additions meant the aircraft would automatically adjust inputs for outsized loads and would keep the aircraft flight stable. I can quite confidently say that carrying a 275-ton max orbiter and tank and then suddenly detaching them would be somewhat difficult without a fly-by-wire system. The final consideration isn't specific to the AN-225 itself, but to air launching in general, and that relates to the actual topic of this video, the engine. At the target launch altitude of 10 kilometers, the air density is only about a quarter of that of sea level. In other words, it's much closer to a vacuum than it is to sea level pressure. A major difficulty in designing, say, the shuttle main engines was building them to operate at both sea level and efficiently in a vacuum. They have large nozzles for vacuum operation, but those required, frankly, a breathtaking amount of design to strengthen them for sea level operation, especially during ignition. With the RD-701 igniting 10 kilometers above sea level, it was essentially operating near or in vacuum for the entire flight. That would have reduced the strengthening needs and brought the mass down, and that, in conjunction with the energy gained from an air launch, a very high chamber pressure, a closed combustion cycle, and optimum choice of propellants, is why this relatively small tank would have been enough to get the orbiter with 2 cosmonauts and 5 tons of payload to low Earth orbit. So, although I don't have all the information available, and quite frankly the capability to calculate whether the AN-225 would have the necessary strength and power to lift max to its launch altitude, with everything discussed in this chapter considered, I'm confident it would have been able to do so with some semblance of practicality. And if all that failed, Antonov proposed adding 2 extra engines. That is something referred to as the AN-325. Though the Russians in the early 90s generally referred to a basic 6-engined AN-225 with the launch suite as an AN-325, I will leave the rabbit hole of further AN-225 and MAX derivatives as an exercise for the viewer. The channel to visit for animations of abandoned launch concepts is Haze Grey Art. They have a brilliant animation of MAX. One of the top comments in that video says, "The collapse of the Soviet Union really screwed up space travel for decades." I don't really think that's true. I find it disheartening that both Western and Russian governments have effectively turned their back on space exploration during my lifetime, but I don't think the Soviet Union collapsing is the only reason that happened. By the turn of the 21st century, there were a few promising ideas in the US that were in the advanced stages of design, namely the Rocketdyne XRS-2200, a linear aerospike engine, and the integrated powerhead demonstrator, a full-flow stage combustion engine fueled by hydrogen. Ironically, I think the main reason we never got to see these engines fly is their amazing progenitor, the RS-25, or more specifically, the vehicle it was mounted on. 2 shuttle disasters forced Congress to commit an almost absurd amount of funding to keep the program flying, as they were essentially mandated to do so in order to complete the International Space Station. Now, the ISS has been a resounding success, but back on Earth, and largely in addition thanks to some absolutely wacky politics, 15 years after the last shuttle flight, NASA are forced to fly an extremely expensive derivative of the shuttle. It doesn't really use any new technologies, and it dumps 4 of those reusable RS-25s into the ocean on every flight. All that said, it is completely unparalleled in payload to orbit capacity at the time of recording. Alright, no, listening back, I want to walk that back a little bit. I've made that joke in a previous video as well, and laughing at SLS, if you want to put it that way, is, well, it's a bit blasé these days, isn't it? SLS is one of 2 rockets ever built that can carry that kind of a payload to low Earth orbit. I suppose 3 if you count Energia, depends how technical you want to get. The bottom line is, nobody knows how to build such a heavy launch vehicle for anything less than an awful lot of money. I do think it would have been a perfectly fine shuttle derivative if maybe it first flew 10 years ago rather than having a gigantic hiatus, or maybe if it was used for something else rather than trying to land people on the moon. We'll come back to that in a video next year, probably, hopefully, after it's flown people around the moon. The Russians, for their part, have also not managed to improve upon the RD-170 and its derivatives. They spent 20 years developing the Angara, which has been mired in controversy and uses the RD-190. But in recent years, there has been a surge in engine development in the US. It's by the private sector. Whether it's a good idea to essentially hand over much of the West's launch capacity to billionaires is an open question. It's one I have no intention of tackling here. SpaceX famously were the first to fly a full-flow stage combustion engine, the Raptor, mentioned at the start of this video. Its dual shaft design is reminiscent of the RD-701, and it certainly shares some commonality with material choices for the oxidizer-rich side. Unfortunately, there's a lot of controversy to skirt around when discussing SpaceX at the moment, and I'm not going there. He doesn't deserve my attention. But some claim they simply copied the integrated powerhead demonstrator and have done nothing new. Even if that was true, which it isn't, all that would represent is both NASA and SpaceX doing their jobs well, NASA taking the first leap and passing the knowledge on to the private sector. All that said, the Raptor is very much in its test phase as I film this video. Time will tell whether SpaceX are able to address the reliability issues. Stoke Space have since developed their own full-flow stage combustion engine. Again, we'll learn whether it's viable over the next few years. Elsewhere, oxidizer-rich closed-cycle methane engines are very much in favour at the moment. All of these can be thought of as spiritual successors to the RD-180. To be honest, I'm already bored of them. I can only hope someone will dig out the kerosene-hydrogen-oxygen tripropellant plans someday. That would require another risky first move. But if you run a private company, why take that risk? By most measures I can think of, Falcon 9 is the best launch system developed during my lifetime, and it uses relatively simple open-cycle kerosene engines. As for air launching as a concept, it's seen limited success but on a much smaller scale than Max. The first successful air launcher was technically the F-15, which demonstrated the ASM-135 anti-satellite missile back in the early 1980s. Some claim this was orbit capable, but I have doubts about that. I'm not able to confirm right now. Recently, Virgin Orbit carried out a few successful satellite launches from a modified Boeing 747 before running out of money. The most successful air launch system to date has been the Pegasus. Launched from a Lockheed TriStar, it's proven itself a reliable, albeit expensive system over its 3 decades of operation. What about bigger payloads? What about that possible competitor to the AN-225 I mentioned earlier? I remember about a decade ago, proposals were floated to strap a scaled-down and modified Falcon 9 to this. This is the Stratolaunch Rock. Unlike the AN-225, it is absolutely hideous. This would have to work hard to win my heart. As is the running theme here, its parent company have since gone bust and been bought out. But following its initial test flights, the AN-225 had an equally rocky, if not worse, few years. Who knows? Maybe the Rock will eventually go on to do great things. After all, just like the AN-225, it's designed to carry a payload of 250 tons.